Okay, here's a nice question we've got here about first harmonics in a tube with open and closed ends. Take a look, and then when you are ready to go, watch the explanation. Okay, it's always a really good idea to have a good understanding, good image in your mind about what the harmonics look like for different situations. So in this case, we've got an open and a closed end. And so hopefully you're envisaging things like this. We should have a node forming, in this case on the left-hand side, and an antinode forming on the right-hand side. So these are what are called the first three harmonics. Here's the first, the second, and the third of a pipe with an open and a closed end. And this is going to be important for you as you try and do this calculation. Now, often we change the wavelength. In this case, we're actually changing the length of the tube. And we're noticing that we're going to access the next harmonic. So let's go for it. Firstly, we know that for the first harmonic, the length of this of the initial tube must be a quarter of a wavelength. And you can see on the screen here, when we have the first harmonic forming, we've got quarter of a wave in there, and so therefore the lengths have to balance out. That is quarter of the wavelength. If we're then going to the second harmonic, we can see that's going to be 3/4 of a wavelength. Now, what we've done in order to go from first to second harmonic, we have added 0.1 meters onto the length of our pipe. So we've made the pipe longer. So hopefully you can understand that what we've done is we've got a new length, which is bigger than L0, the original length, by 0.10 meters. Okay, then what we're going to do is we're going to take these equations. We notice that if I subtract, in this case it's the top equation from the second equation, I'm going to end up with the fact that 0.10 is equal to half of a wavelength. And so in other words, the wavelength there is equal to 0.2 meters. As such, that means our answer here is C.